Ladies and gentlemen, let's talk a little bit about non-targeted screening in environmental chemistry. This is a joint presentation of Lomonosov Moscow State University in Russia and the LECO Corporation in the United States. Collaboration started about 15 years ago, and during the last 10 years we worked in various fields, and one of those fields is the non-targeted analysis of the environmental samples. Mainly we were working with the precipitations, I mean snow and rain. Snow gives you a chance to estimate long-term pollution of the atmosphere of the site of the sampling. For example, in Moscow, this is about 4 months. So collecting samples in March, you can get information about something like 4 months contamination of the air. With rain, it's different because analyzing rain, you get information about air contamination in this particular site and in this particular moment. Today, I'm going to give some results of our studies conducted in the Russian Arctic. We had 2 expeditions to Novaya Zemlya Island and to Franz Josef Land. And panorama of those places is like that. This is summertime. Another big territory is Moscow, the capital of Russia. It is very interesting place to study atmospheric pollution because this is the largest European city, and we have something like 7 million cars. We have about 700 enterprises and many other sources of possible pollution. Here you can see, by the way, the daytime at the Moscow Belt Road, and here nighttime at the Moscow Belt Road. You may say it's quite beautiful, but once I was entrapped in the traffic jam for 8 hours in winter, and I can assure you it wasn't pleasant at all. Anyway, several times we collected snow samples, and we were doing that along the perimeter of the Moscow Belt Road and also radially, beginning from the heart of the city near the Kremlin and along those radians to the Moscow region. We also had several samples of rain collected in Valparaiso in Chile, and the sampling site is just on the coast of the Pacific Ocean. And finally, we had samples from the cloud water collected at the mountain Puy de Dôme, which is just in the middle center of France, nearby the city Clermont-Ferrand. And here you can see the station, the laboratory where the samples were collected. So we used different methods of sampling, and for example, it was very professionally in France. They had special cloud impactors, and they collect really water when cloud appears at the sampling site. We had more or less sophisticated instruments in Chile, and in Moscow, for example, for rain sampling, we used a very simple device like that, and you put it at the roof of the building and you collect. With snow, you behave a bit differently. You use such kind of pipe, and it is very important to pick the snow up to the ground to be able to get really long-term contamination information. And then we used classic US EPA 8270 method sampling preparation approach with dichloromethane. For almost all the examples I'm going to show you today, we used the final version of the LECO instrument, which is represented here at this slide. And the most important features I am going to demonstrate are efficiency of high resolution and high mass accuracy, a GC-GC tool, and complementary ionization tools for each analysis. So some parameters of the instrument are mentioned here. You can see the extended mass range, and you can see very nice mass resolution, mass accuracy, up to 200 spectra per second you can run using GC-GC tool, and very nice sensitivity of the instrument and quite nice dynamic range for. For the majority of samples, we used this multi-mode ion source, and it is quite interesting innovation because it contains two chambers. One with low pressure is used for electron ionization, and another closed one is used for chemical ionization. And usually when you use electron ionization, the orifice for chemical ionization reagent gas at the left is closed, and the compounds are coming from the chromatography column through the transfer line, and ionization takes place in the right part of the ion source, and you get normal electron ionization mass spectra. If you would like to carry on chemical ionization analysis, you open the orifice for the chemical ionization reagent gas at the left side, and you do ionization in the left part of the ion source with a higher pressure due to reagent gas, and you get either positive chemical ionization reactions or electron capture negative ionization mode you use. Everything can be achieved quite easily without any reconstruction of your instrument. So here you can see examples of 3 samples of snow collected near Moscow State University. This is pretty clean part of Moscow, but anyway, and here you can see something like maybe 50-60 peaks, chromatographic peaks. Looks like not something terrible. And okay, but if you use zooming, you get the picture like that, and you understand that in fact each sample contains not 70 but maybe 700 or even over 1000 individual peaks. And the idea of non-targeted analysis is to try to identify as many as possible of them. So it's not easy. But anyway, with the tools provided by LECO machine, we succeeded in many cases. I would like to start with accurate mass measurement. The first pictures. Here you can see low resolution and high resolution picture for the detection of tetrachloroethane. The same low resolution and high resolution for the detection of caryophyllene terpene in plant extract. So I don't think that you need any comments, because obviously that we have very nice peak here, and it's possible to do quantification and no result at all with low resolution. This analysis was done with very old prototype of modern LECO instrument, something like 10 years ago. But I really like this picture and show it in my lectures. Here again, this is a snow sample, and this is just mass spectrum without any chromatographic separation of the components. So direct introduction of the sample, and very low mass range, just integer number 252. Why this mass? Because this is the molecular ion of benzapyrene, very known carcinogenic compound regulated all over the world. But what is interesting, everywhere, so I would say 99% of methods, this compound is detected using 252 ion, integer mass. But look here, we have 13 different peaks with the same integer mass, but different exact mass, meaning that we have 13 different elemental compositions. And I would like to emphasize that elemental compositions, not individual components. And it means that each of those elemental compositions may be represented by 1, 3, 5, 10 individual compounds, isomeric compounds. And then we have, even in this quite simple compound, a quite simple sample of snow, we can have something like 100 individual compounds giving 252 ions in conditions of electron ionization. And look, if at least one of those compounds has retention time close to that of benzopyrene, you're in a big trouble because you get false positive result. And when you are dealing with such nasty compound as benzopyrene, it's not possible. So definitely having accurate mass measurements, you avoid this very, very dramatic mistake. Now some examples. First of all, I should say that I'm going to show you the most difficult cases, because if we are dealing with a nice chromatographic peak, no problems, because we have a very nice mass spectrum and we have good heat table, and you can easily understand what you are dealing with. But if you have some very small peak, something like that mentioned by the arrow, with very bad signal to noise ratio, your mass spectrum looks like that at the bottom. This is peak true, so after processing. And then you ask, and now look at the hit list. Hit number 1 with the best score, it has correct nominal mass. But the exact mass is wrong, meaning that this is not the compound present in our mixture. So we have to go down along the hit list, and only hit number 26 has the right exact mass of the molecular ion. So we're dealing with dimethyl naphthalene, probably not 1.2 dimethyl naphthalene, but definitely with an isomer of dimethyl naphthalene. So all the previous hits, I mean 25 hits with beta scores, are wrong. And it is very important because some of those compounds are really not very pleasant. They are different barbitals, so biologically active compounds, and you could make serious mistake if you select some of them. But having information about exact mass, you avoid all those mistakes. Another story. Look here. So the spectrum of some component of snow sample, and I should say that preliminary, we used to run samples using some simple GCMS system, low resolution. And when we got this best hit, 2-methoxyfurane, as the best hit in the case of that compound, we thought that it is fine because we had something like 20 other furanes in this sample. Nothing was something special. But when we ran accurate mass measurements, we got the following result. The exact mass of this compound, 2-methoxyfurane, was wrong in comparison with the exact mass of our component. And again, we had to go down along the hit list, and correct mass was found only in hit number 21, which is 4-methylpentanone. Again, I am not sure that we were dealing with this particular isomer, but definitely it was an isomer of this pentanone, and not some furane or some other isomer with different elemental composition. So again, we managed to avoid a serious mistake in identification of the compound. One more example. Very small peak here, but mass spectrum was quite nice, and that's why we decided to try to identify what was that. The hit list you can see here, and again, exact mass for the best hit was wrong, and you have to go further along the hit list down, and only hit number 43 contained correct mass value, and it is this naphthothiophene. But I think that we had dimethyl dibenzothiophene, which has the best hit of this isomer was number 74. Why do I think so? Because all the previous peaks, quite big peaks, with retention time around 890 to 900. Those were different isomers of dimethyl dibenzothiophene. And the last one, which is really very small, should be from that company and not something else. Look, hit number 74. I wonder how many of you go so far along the hit list trying to find the correct answer for your solution. We managed to find quite a number of very interesting compounds. Just one example, look at this nickel-containing compound. I didn't think that this compound could pass the column, but it passes the column, and definitely it is what is mentioned here, because the library score is very nice, and accurate mass measurements confirm the identification. Moreover, we found out that this compound is added into the tires of trucks, and that's why a lot of high levels of this compound we can find nearby the highly used roads. Sometimes software, I mean, you can achieve the result using a mathematical approach. For example, here you can see mass spectrum recorded at the top of the chromatographic peak, and as you can see, the spectrum is quite rich. Iron with mass 177 could be considered as a possible candidate to be molecular iron. Immediately software allows getting information about all other ions which could be considered as fragment ions of this molecular ion. And we get the following table where we can see that those four, number 13, 14, 10, and 11, are not fragment ions of this molecular ion, so they belong to some other compound. So we reconstruct mass chromatogram using the masses 177 and 146, and we get the following picture. Look, definitely we have two different compounds, but their retention times are extremely close to one another. It is something like 100 milliseconds. Nevertheless, software allows separating those two chromatographic peaks and get two different subspectra. Then we have to use those subspectra to check, to carry on library search, and we get quite nice result that the first one is an N-diethyl carbamiditioic acid and the second is coumarin. So even those very difficult cases can be very nicely and efficiently resolved using the software and measurements. We also can avoid bad mistakes using a higher resolving power. Look here, for example, with 2 decimal points, we got the following extracted ion chromatogram. This is actually the mass of the most nasty compound known to analytical chemists, tetrachlorodibenzodioxins. So definitely it's not very pleasant to have such nasty compound in the atmosphere of any city. So should we start alarm? No. If we do really high resolution analysis with accurate mass measurements and measuring ions with 4 decimal points, we get information that no, those compounds are something different, not tetrachlorodibenzodioxins, and so we don't need any alarm. Very, very important result. Working in the field of non-targeted analysis, you should be aware that sometimes the new compounds you are going to find are not possibly present in the modern library. And several examples of this kind. Look at this peak. Again, very small chromatographic peak, but mass spectrum was quite nice. And even the mass of the best hit, which is vinyl benzoate, was correct. Another correct mass was with hit number 9, which is this propanedione. And here you have, this is the spectrum of our component in the snow sample. This is the best hit, and this is hit number 9. Look, molecular ions are everywhere, and the mass is correct. And the majority of peaks are here, but in our case, we had this 133, which was not present in both spectra of possible candidates. Since we know elemental compositions of all those peaks due to accurate mass measurements, we can understand that the molecular ions of those compounds, they eliminate methyl group and then consecutively 2 CO molecules. And knowing the rules of fragmentation, it was not difficult to propose the following structure of acetyl benzaldehyde. We work at the organic chemistry department, so it was quite natural we synthesized this compound. It was not in the library by that time, and we proved that our decision was correct, and we had this particular compound in the Moscow. Another example, peak 151 could be considered as possible molecular ion, and we could even say that it contains 1 chlorine atom. However, ion 133 interferes with this hypothesis because the difference between 133 and 151 is only 18 mass units, and 133 doesn't contain any chlorine. So we reconstructed ion chromatograms for 133 and 151, and you see there is some difference in the retention time. So 133 belongs to another component. Eliminating this peak from the consideration, we can really understand what we had. We know exact masses of all the fragment ions. Then we know the elemental compositions of all those fragment ions. And using the rules of fragmentation of organic compounds, it was not so difficult to propose the following scheme of fragmentation and the following structure of the molecular ion. Now let's go to GC tool. Here you can see a nice picture provided by Ryan Rogers a couple of years ago. And this is, by the way, one of the most sort of rich spectrum or chromatogram, because here they managed to identify 12,000 individual compounds. What is also very important, different groups of compounds occupy different positions at this 3-dimensional chromatogram. Another, benefit, it is very beautiful. I believe you agree with me. And I really enjoy working with results like that because it's sort of, they give you aesthetical pleasure and you really work more efficient. Anyway, a couple of examples. Here you can see a mass spectrum of a component of cloud water collected in France. Peaks with masses 100 and 112 could be considered as molecular ions of two different compounds, or they could be treated as fragment ions of something heavier. We reconstructed mass chromatogram using the masses of those ions, 112 and 100. And look, their retention times are the same, so we couldn't resolve the problem. However, when you add the second column, polar column, you get two separated peaks. And then you have two nice mass spectra. You can carry on very efficiently library search and you get the final answer. We have two furanons. Another example, Arctic snow. Look at that chromatographic peak, number 63. Looks like individual, nice, intensive peak. Should be easy to understand what is the component. However, mass spectrum recorded at the top of this chromatographic peak doesn't look very spectacular. It is in the middle, peak true, and definitely contains some impurities from other coeluting compounds. Heat table, look at it, quite nice scores, close to 800, but anyway I didn't like the names of those compounds. When we used two-dimensional GC, we got the following picture. This is separation of this individual peak in orthogonal direction. So you can see how many compounds are there. And look now, we can see here the first one was chromatographic phase. The second one is alkane. The third one is butylbenzene, one of the isomers. Then acetophenone. And finally cresol. So instead of one erroneously identified compound, we have four very relevant from the environmental point of view compounds. They are definitely pollutants and we should be aware that they are present in the sample. Great! Instead of one erroneous, four relevant peaks. Another important benefit of GC-GC is position of the peaks. For example, alcohols and naphthenes give very similar mass spectra due to easy loss of water molecule by alcohols. However, when you work in GC-GC mode, since alcohols are more polar, they appear in a different place of this two-dimensional chromatogram. And just knowing the position of your peak, you can say that you are dealing with naphthenes or alcohols. 2 years ago, we proposed an algorithm to calculate retention indices along the second short column. And we can use either full version of those indices or restricted version. And I like the second variant even more because you get all the isomers and homologs in one line. And it is very important because you do not miss any minor components of the same type in your sample, even if you miss them preliminary studying the whole information about your sample. Very good example, analysis of an Egyptian mummy. The mummy is in the Pushkin Museum in Moscow, and we try to identify as many components used for mummification as possible. And here we were dealing with fatty acids. Look, the line formed by the images of homologues of fatty acids with a retention time about 0.8. You can get all the information about all those homologues, even if you miss the smaller peaks during the preliminary study of your spectrum. And above the first line, you can see another line with retention time about 1. And this line is due to dioic acid, which is also very important for the characterization of these mummy samples. So two types of acids are very nicely visualized using this approach. Now to alternative ionization tools. Let's start with positive chemical ionization. And phthalates represent very nice example what can be done using positive chemical ionization. Phthalates are very well known environmental pollutants and they're present all over the world. Nowadays you can hardly find a sample without any phthalates anywhere in the world. The peculiarity of electron ionization of phthalates is the formation of ion of M to Z value 149, which is represented here. It is very intensive ion in the mass spectrum. And so when you would like to find all the phthalates in your sample, you just reconstruct mass chromatogram using the current of this ion, 149. Some of the phthalates are already in the list of priority pollutants in many countries, and you have the standards of those phthalates. However, you usually have more phthalate peaks than you have the phthalate standards. And then you have to identify what are other phthalates in your sample. However, the problem with electron ionization deals with the fact that molecular ions are absent for phthalates in electron ionization. And in that case, you cannot understand what are you dealing with. And here, chemical ionization may be really very helpful. Look, here mass chromatograms reconstructed using electron ionization or chemical ionization. They are quite similar. So no problems you are dealing with electron ionization or chemical ionization. And then you come to mass spectra. Look, they are quite different. But nevertheless, 149 you can see in electron ionization mode and in chemical ionization mode. Moreover, you have molecular ion, or better to say, protonated molecule peak in chemical ionization mode. So you get information about molecular mass and you get a lot of information on fragment ions. So having the knowledge of fragmentation of organic compounds, you can derive the structure of the whole molecule. Look, for example, at this scheme. One of the phthalates we had in our sample didn't have molecular ion in electron ionization, but it had a protonated molecule in chemical ionization mode, and its M to Z value was 335. So, knowing the rules of fragmentation, we could derive the structure of this ion, and it was butyl-octyl phthalate. So very helpful method, I mean positive chemical ionization, when you don't have molecular ion in the spectrum of electron ionization of your compound of interest. Situation becomes even more interesting if you use electron capture negative ion mass spectrometry. Look at this example. We have a mixture of 3 compounds. The concentrations are the same for all 3 of them. Nevertheless, in the case of electron ionization, we can see only the benzofurane, no peaks of dinitrophenol and pentachlorobenzene. On the other hand, in electron capture mode, we see particularly those two compounds, dinitrophenol and pentachlorobenzene. But we don't see any peak of dibenzofurane. So definitely very nice and efficient complementary tools. Electron capture gives you a chance to distinguish between isomers. Look how different is the sensitivity of this method in the case of isomeric phenanthrene and anthracene. This is a standard solution of phenanthrene, anthracene, and deuterophenanthrene, which is used as internal standard. We don't see phenanthrene in the case of electron capture ionization, but the peak of anthracene is higher than in the case of electron ionization. Great. Same with many other polycyclic aromatic hydrocarbons. For example, you are interested in chlorinated compounds in your mixture. In this case, you reconstruct mass chromatogram using the current of chloride ions. This is reconstructed mass chromatogram in positive mode, electron ionization, almost nothing. It is empty. But in the case of electron capture, look, over 100 individual peaks. And then clicking at any particular peak, you can get information about molecular mass and some structural features of those compounds. Great. Same with bromine. Just one loosey peak here and about 50 individual compounds in the case of electron capture. And look at the intensity of those peaks. Just 70 here and 30,000 here, so almost 1,000 more sensitive method. And surely it's very important when you are looking for some halogenated compounds. Polychlorinated biphenyls, very important class of environmental pollutants. Look at the results in electron ionization mode, just 3 peaks with the intensity 700. And in the case of electron capture ionization, you have all the isomers presented in your chromatogram. Besides, the intensity is 70,000, so 100 times higher. Definitely, this is the method of choice when you are dealing with those compounds. We couldn't find any peaks of heptachloro or octachlorobiphenyls with electron ionization. With electron capture, no problem to carry on even quantitation. Only if you're eager to say that you really found dinitrobenzene in your sample, you show this picture in electron ionization mode. But in electron capture, look, 3 beautiful peaks of the isomeric dinitrobenzenes with very, very high intensities. This is almost 1,000 times more efficient. Same with dinitrotoluenes. 2 peaks here and the intensity is 1200, and all isomers you can detect here and the intensity is 500,000. So definitely besides information on the molecular mass, electron capture ionization gives you a chance to get some structural information because you have a number of fragment ions responsible for the main structural fragments of the molecule. Electron capture ionization allowed discovering in Moscow snow samples collected last year quite a number of compounds from the dirty dozen. Actually, we didn't detect those compounds during the last probably 25-30 years in Moscow environmental samples. And that was due to the very low concentrations, levels of those compounds in the environment. Nevertheless, When we increase the sensitivity of the instruments using electron capture, we manage to get this information. For example, this picture represents a mass spectrum of beta endosulfan, one of dirty dozen components. And you get molecular ion and you get some fragmentation. Besides, we detected two isomers of those compounds, as it should be for the commercial product containing alpha and beta endosulfan. Another example, two coelutin peaks. The difference is just 1 second. However, the use of the convolution procedure allowed getting two individual mass spectra. And the spectrum named B represents DDE, the most stable metabolite of DDT. And spectrum A looks like dieldrin or aldrin or another isomer of those particular compounds. However, for knowing the retention time of DDE, we could easily understand that we are dealing with dieldrin because its retention time is almost the same as that of DDE. It was really interesting. Finally, another example where all three issues were used together. So this is a three-dimensional, so GC-GC mass chromatogram based on the ion current of iodine anion in electron capture mode. Again, this is a mummy sample, and all those peaks represent iodinated compounds, and presumably they are components of sea plants which were used for embalming procedure during mummification. So, coming to the conclusions. Accurate mass measurements allowed for better sensitivity and reliability of the targeted analysis, high efficiency of non-targeted analysis, and spectral elucidation. GC-GC tool significantly increases informational capacity of the analysis, provides cleaner mass spectra, allows grouping of homologues and isomers. Positive chemical ionization allows obtaining molecular species, resulting in higher reliability of their identification. Electron capture negative ionization increases sensitivity over 100 times for polyhalogenated and nitro compounds. And finally, complementary use of electron ionization, chemical ionization, electron capture negative ionization, and GC-GC allows increasing identification score almost twice, significantly increase reliability, decrease the number of false positive and false negative results. Thank you for your attention and questions, please.